In Unit 12 on quantum and nuclear physics, we're going to take some of the ideas that we covered in Unit 7 just a little bit further. Subtopic 12.1, we're starting off looking at the interaction of matter with radiation. Now, the radiation that we're talking about here is not nuclear radiation so much, it's more electromagnetic radiation, so electromagnetic waves. The first concept that we're going to talk about is that of the photon. We've already sort of looked at what a photon is, but we're going to just sort of fill in a bit of the backstory a little bit here, just so you've got a better idea of what we're dealing with and how we came to understand what a photon is. And basically, we're going to go back to Newtonian physics. So that's the physics that Newton was largely involved with. And back in Newton's day, light was treated as a particle. And in treating it as a particle is basically the idea that as it reflects, it sort of bounces off. And so a few other phenomena that when you observe light, it looks like it travels in straight lines. So it looks like it's somewhat of a particle. But we know that that was sort of thrown on its head a little bit with Young's double slit experiment. That suggested that light actually had wave properties. And we've already dealt with that in Unit 4, or is it Unit 9? So with Young's double slit experiment, showed that light behaves as a wave. So we've got this interesting scenario now that we started off with a particle understanding, and then we move forward into Young's double slit experiment, and we see that light behaves as a wave. So if we look at classical theory then, so still dealing with Newtonian physics, there are certain properties that we would expect to see about electromagnetic radiation. And if we're dealing with light being a wave, we would then explain that light being an electromagnetic wave means then that that's going to be produced by the oscillation of a charged particle. So when we're dealing with electromagnetic waves, whether that's light or X-rays or gamma rays or whatever it might be, radio waves, we're dealing with the oscillation of a charged particle. And that then has certain flow-on effects as to how we would measure some of the quantities associated with that wave. That would then mean that the higher the frequency, so if we're dealing with the oscillation of the particle, of a charged particle, the higher the frequency, the shorter the wavelength will be. And if we've got a really short wavelength, that means that there's a lot of energy being input into the system in order for the oscillation to occur. So that means we'll have a lot of energy being radiated, and that would then mean that the expectation that we would see, so based on that classical theory, the expectation, if we were to look at a graph of energy versus wavelength, so as the wavelength increases, we would expect there to be less energy. So when it's a very short wavelength, so energy on the vertical axis, we'd expect a relationship that looks something along those lines. So for very short wavelengths, closer to the vertical axis there, we'd expect very high energy, and for very long wavelengths, we'd expect very low energy. Interestingly though, the observation that we saw didn't quite match that. And the observation that we're dealing with here, I'll jot down some notes in a second, but what was actually observed was a graph that looked something a little bit more like that. And so this observation, as often happens in physics, the observation didn't match the expectation, and so the understanding there had to be revised in order to explain what was actually going on. Now, the observations that we're talking about here are of black body radiation. Now, when we're talking about black body radiation, we're not talking about objects that are black. When we're dealing with black body radiation, we're dealing with hypothetical objects that absorb all electromagnetic radiation that falls on them. It doesn't reflect any of it, hence the name black. If it's absorbing everything, then it would appear black. So it absorbs all the radiation that it falls on it and then re-radiates it. So it's not reflected, it's re-radiated. Now, talking about it being hypothetical, there are some objects like stars, for example, that are very close to being blackbody objects. So there are some very close approximations, and by observing those blackbodies, it showed that low energies were radiated at short wavelengths. So that totally contrary to what was expected for classical theory, and it led to this term. It's an interesting term. So if we look at these wavelengths here, it basically gives us this phenomena that's now referred to as the ultraviolet catastrophe. The idea being then that if you have shorter and shorter wavelengths, then you get a ridiculous amount of energy being produced in the UV spectrum. So just as an interesting side note there. Now, I think this is one of the most interesting stories in physics. Max Planck actually came up with a solution to this problem, or a solution to the understanding behind it, and he suggested that with a mathematical alteration, so he basically sort of came along and went, hey, if we do this bit of maths on the theory, we can come up with an explanation that actually sort of fits the observation. So this mathematical observation or mathematical alteration that he made, he didn't actually think it meant anything in the physical sense. It was literally just a mathematical trick sort of thing that he performed in order to make sure that the observations and the theory matched, but he didn't actually think it had any physical meaning. And the observation, the alteration that he made, resulted in electromagnetic waves only radiating energy in certain amounts. So only radiating energy in quantized amounts, or in multiples of a quantized amount, I should say. And when we say a quantized amount, we're really saying that it's a small discrete amount that can't be any smaller than that. So it's the smallest possible amount. So a small quantum of energy, or a small discrete amount of energy. And so, like I say, didn't think that really made any sense in a physical sense, because how could you have these quantized amounts of energy? Energy is continuous, so it's just got to be a mathematical thing. It wasn't until Einstein came along and applied that to a phenomena that we'll look at in the next video, that showed that it wasn't just a quirk of the maths. It was actually there was a physical interpretation. And that interpretation led to the concept of a photon. And as we've discussed previously, a photon, we can consider that to be a packet of energy. So now we've got this wave nature of light, or certain phenomena that can be related to the wave nature of light, but we also have these phenomena that relate to the particle nature of light as well. And we'll explore that in a bit more detail in the next video.